RAD 107. All right, we're in week 3, chapter 2. We talk about digital imaging characteristics. Okay, so you have the video I'm recording going to be here. Then we have the PowerPoint. So this is the author PowerPoint, my PowerPoint, and then my study notes. Let's jump right into it. So, skipping over the objectives, should be pretty simple. Pretty simple PowerPoint, pretty simple chapter, a lot of memorization and just kind of understanding what the concepts are. So analog images versus digital images. In medical imaging, there's two types of images, analog and digital. Analog refers to a device or system that captures or measures a continuously changing signal. Digital is recorded as multiple numeric values and is divided into an array of small elements that can be processed in many different ways. I'm a really good reader, huh? So this is pretty much how this chapter is going to be, just knowing the terms. So analog is not really, so analog signal is a wave. Typical analog device is a watch with the hands continuously moving around the face. It's capable of indicating every time of the day. In contrast, a digital clock is capable of representing only a finite number of times, every 10th of a second, for example. So the watch can show, analog can show more detailed than, this is kind of infinite, this is finite. So your best friend, as usual, are the study notes. So if you go here, you click these study notes, pretty much breaks down the PowerPoint into a chart, so a table. So you kind of know the most important stuff, and it's all in here, and it's much easier to digest, in my opinion. So it's up to you. Use the PowerPoint or this, but if you focus on this, you'll have no problem with the quiz. All right, so let's talk about pixels. What's a pixel? A pixel, or a picture element. So a pixel is actually, I didn't know this for a while, a pixel is a acronym for picture element. It's the smallest element in a digital image. That's what a pixel is. So these are all little pixels. Pixel size is the number, the smaller the pixel size, the higher the spatial resolution. So this is one that you guys are going to want to put into your comparison and contrast table. Pixel size, the smaller the pixel size, the higher the spatial resolution. A lot of things have an effect on spatial resolution. One of them is pixel size. Pixel bit depth is the number of bits or pieces of information within each pixel. Okay, there's a formula for this. It's basically the number of gray tones that a pixel can produce is 2 to the power of bit depth. So if a pixel has a bit depth of 8, then the number of gray tones that a pixel can produce is 2 to the power of 8, which is 256 shades of gray. Okay, so this is some math that you guys will need to know. Super simple. You'll be asked, what's the number? How many shades of gray can this bit depth produce? So you get the bit depth as 8, 2 to the power of 8. If the bit depth is 10, 2 to the power of 10. The bit depth ranges for most systems from 10 to 16. 10 to 16 is the bit depth, or 2 to the power of 10 to 2 to the power of 16. So shades of gray would be 1024 to 65,536. Okay. Pixel bit depth. This is kind of what makes a difference here, what it looks like in real life. 2 shades of gray versus 16 shades of gray versus 256 shades of gray. Matrix. What is the matrix? Slow motion stuff, right? The matrix is a square arrangement of numbers in columns and rows. In digital imaging, the number corresponds to a discrete pixel value. So a matrix is basically a bunch of pixels. Each box within the matrix corresponds to a specific location in the image and a specific area in the patient's tissue. The image is digitized by position and by intensity. So position is the spatial location and intensity is the gray level. Typical number of pixels in a matrix ranges from 512 by 512 to 1024 by 1024. Size of the matrix determines the size of the pixels. So if you have a 10 by 12 and a 14 by 17 CR cassette and they both have a 512 by 512 matrix, the 10 by 12 is going to have smaller pixels. You might have to read that a couple times. For a given field of view, the larger the matrix size, the greater the number of smaller individual pixels. Increasing the number of smaller pixels will improve the quality of the image. So the smaller the pixels, the better your image. So if you have a large matrix and a small matrix, so the same size here, we have one has small pixels, one has larger pixels. So you can see the one with the smaller pixels, you can identify more areas within the image. It's not as choppy. Field of view. Term field of view is synonymous with the X-ray field. It's the amount of body part or patient included in the image. The larger the field of view, the more area is imaged. Changes in field of view do not affect the size of the matrix, but changes in the matrix affect pixel size. As the matrix increases, the field of view remains the same. So you would be doing yourself a huge favor to start putting these terms in one table so you can compare and contrast, because there's going to be a lot of them. So field of view. So here's how they compare. Matrix size can be changed without affecting field of view. Field of view can be changed without affecting matrix size. A change in either the matrix size or the field of view will change the size of the pixels. Exposure indicators. Exposure index refers to the amount of exposure received by the image receptor, not the patient. So this is that like S number that you guys might see in clinicals. Manufacturers differ in the way exposure is numerically represented, so it could be difficult to calculate. Remember we talked about that, that you can't, there's no set, we can't say this S number is right because every manufacturer is going to be different. Standard units of measurement. Again, go back to this here. Air kerma, standardized radiation exposure, KSTD, indicated equivalent air kerma. So just know these in the chart, it makes life way easier. We'll go through them real quick. Air kerma is the measurement of radiation energy absorbed in a unit of air. Standardized radiation exposure, K-standard, is a standard exposure typical that an imaging receptor. So KSTD is the typical expected exposure of an empty IR. It's the main thing you need to know. KIND is the measurement of the actual exposure of a body part on the IR. So this one is an empty image receptor. This one is an image receptor with a body part on it. It's kind. And then K-target is how much the kind, KIND, should be for a specific body part and view. So the K-target, they have, for a chest x-ray, it should be this much. The KIND should be this much. For a foot, it should be this much. So that target is how much the KIND should be for a specific body part. It's a target equivalent air kerma. The deviation index, DI, is the difference between the K-target and the KIND. That's how far off you are from where you're supposed to be. All right. Let's see. Brightness, contrast resolution, and spatial resolution. Brightness is the appearance of the image on a monitor. Nothing you can do about brightness. It's really the monitor. Okay, it's not. We're not talking about contrast or density. This is the actual monitor. Contrast resolution refers to the ability of the digital system to display subtle changes in the shades of gray. It's directly related to the bit depth. Spatial resolution is the ability of the imaging system to demonstrate small details of an object. Smaller pixels gives us higher spatial resolution. So, for example, an AP knee does not show the soft tissue on a lateral, on kind of the edges here. So here's the difference here with a wider dynamic range. So dynamic range of the image does not equate to higher resolution, it's higher spatial resolution. So dynamic range is basically more shades of gray. Modular transfer function, don't worry about this too much, just know that it's the ability of a system to record available spatial frequencies. That's all you need to know. Noise is anything that interferes with the formation of the image. Radiographic noise occurs during the acquisition of the image. Equipment noise is caused by detector elements, and it's also referred to as quantum noise. Here's what noise looks like, just like this scatter look. And that's pretty much it. So exposure latitude is a range of exposure values, and detective quantum efficiency describes how efficiently a system converts the X-ray input signal into output image. Any questions, shoot me an email. Go ahead and take the quiz. You guys should be good to go. Like I said, go through this. This is your best friend. And I will see you guys next week.